Okay, so one of the key concepts that we learned in the last class is that when we are looking at collisions, we have conservation of momentum. That is, whenever you have a system of particles that are interacting with each other and there's no net external forces acting on that system, which is what we can assume during the collision, because the collision forces are usually way bigger than any external forces, then the total momentum of the system just before they collide will be equal to the total momentum of the system just after they collide. Okay. The code is 5450, I believe. All right. So with that in mind, we did some example problems in the last class, and now we will come to a new topic, which is that in studying these collisions, it becomes useful to classify them into two types. There are the so-called elastic collisions, and then there are the so-called inelastic collisions. And the difference is that in elastic collisions, in both of these collisions, again, momentum is conserved. The total momentum of the system is conserved, as we just saw, whether it's elastic or inelastic. But in elastic collisions, there's the additional condition that the total kinetic energy of the system is also conserved. So right before the collision, the two particles may have some total kinetic energy, 1/2 mv1 squared plus 1/2 mv2 squared. And then after the collisions, when they bounce off, they will also bounce off with the same total final kinetic energy. Again, the two of them may have different kinetic energies in the end, but their sum will be the same as the sum before. Okay. So in elastic collisions, the total momentum and the total kinetic energy of the system is conserved, whereas in inelastic collisions, only the total momentum is conserved, but the total kinetic energy system is not conserved. So that is right after the collision, if you add up the kinetic energies of all the particles, the sum will be less than the total kinetic energy that there was before the collision. And note that the total momentum of the system is conserved in both cases, but kinetic energy is only conserved in elastic and not in inelastic. And you can see here, this picture is an example of an inelastic collision. If you were to, and that's because a lot of the energy in the collision went into deforming the cars, into heating up things and so forth. So they're not gone into kinetic energy of all the final particles. And so therefore that is an example of an inelastic collision. So here's an example of an elastic collision. So these two things will collide. You add up the kinetic energy of this guy initially plus the kinetic energy of this guy. And after the collision, if you add up their kinetic energies, it'll be the same as before the collision. So that's an elastic collision. Then within inelastic collisions, there's a special subclass called a perfectly inelastic collision. And a perfectly inelastic collision is one where after the collision, the two objects that collide, they stick together and they move as one object together. So you can think of two pieces of putty. If you collide them, they will stick together and they move as one object. That is called a perfectly inelastic collision. A more interesting example is when a meteorite collides with the Earth, it gets buried in the Earth, and then the two things move as one system. So that is an example of a perfectly inelastic collision. So next time you see a little meteor shower, be like, hey, we may have a perfectly inelastic collision. What a beautiful night. Anyway. Any questions on that? So in some sense, perfectly inelastic collisions are messier. But from the point of view of like doing web-assigned problems, they're actually easier. Because if I look at the, first off, energy is not, the kinetic energy is not conserved. So you have one less equation to worry about. You can't use it. So in that sense, it's simpler. The only thing you can think about is the conservation of momentum. And so here in this perfectly inelastic collision, these two particles come, they collide, and now they stick together. And this combined system moves as one object with some common velocity. So if I were to apply momentum conservation, then the total initial momentum of this system is going to be m1 v1 initial plus m2 v2 initial. And if they're moving in opposite directions, then one of these velocities will be negative, the other one will be positive because they're moving in opposite directions. But whatever, there's some total initial momentum. And then after they collide, the total momentum of this is that because this is moving as one object, it has a total mass of m1 plus m2 because the two things stuck together. And they're moving with a common velocity, so it'll have a final common velocity of Vf. So in some sense, it's very simple to solve. If you know the initial momenta of the two particles, then you can easily solve for the final velocity in a perfectly inelastic collision if they stick together. The attendance code is 5450. All right. Okay, so here's a top hat question to think about. It's a little bit, it's a bit non-trivial, so think about this carefully. We are told that in a perfectly inelastic one-dimensional collision between two objects, which of these conditions alone is necessary so that all of the original kinetic energy of the system is gone after the collision? Meaning that in a perfectly inelastic collisions, when you collide two things, they stick together. But what you want to happen is that after they stick together, you want them to just be at rest. You don't want the combined thing to move. So if I collide two things, they stick together and come to a stop altogether, then which one of these following conditions must be true in order for that to happen? So I'll give you guys a moment to think about that. The things to think about is that in perfectly inelastic collisions, momentum is conserved. And if the two things at the end are stuck together and they're sitting at rest, then think about what is the kinetic energy of that final thing together, and use those two things together to see if you can figure out which one of these things must be true. Any questions on that? All right, let me go to top hat. Here's that question again. Three seconds. All right, let's see what we got. All right, looks like most of you got the correct answer. The two objects must have the same momenta with the same magnitude but opposite directions. That is indeed correct. And let me quickly go through the logic of that So the idea here is that you want these two objects. Here's object one, there it's coming in. Here's object two, it's coming in. And in the end, you want the two things to stick together and just sit there with zero speed, right? So you just want all the kinetic energy of the system is gone. So for all the kinetic energy of this system gone means that this thing is at rest after the collision, right? If this thing is at rest, then what does it mean? What is the total momentum of this blob right here? If it's at rest, its total momentum is zero, right? Because its final momentum here, which is the M1 plus M2 times VF. If this thing is at rest, the VF is zero, the final momentum is zero. Well, we have conservation of momentum. So if the final momentum is zero, this implies that the initial momentum must be zero. So the total initial momentum, this is P final total, P initial total, which is equal to P initial of particle 1 plus P initial of particle 2 must also be zero, which means that the momentum of particle 1 and the momentum of particle 2 must have the same magnitude, but opposite directions. They have opposite signs, and they exactly cancel. So if you want the two things to stick together and just stay there, you're going to launch them at each other with exactly equal and opposite momentum. Not equal and opposite velocity, because velocity is not conserved. It's momentum that's conserved. And momentum is mass times velocity. Any questions on that? Okay. So this will be the last problem that we do in this chapter, and it's a pretty interesting problem. It's called the ballistic pendulum. Did you guys do a lab about this yet? In Physics 1 lab? No? You all did not do a lab on the ballistic pendulum? Huh, okay. All right, so, well, so, you know, on one of those crazy shows on the History Channel, sometimes they'll bring in a ballistics experts to talk about things. This is kind of what they do, although maybe today they have more sophisticated technology, but at least maybe in the last century, this is the kind of stuff they would do. So here the idea is, it's kind of a remarkable thing. Someone here fires a bullet that goes and embeds itself into this block of wood that is like hanging from the ceiling with some rope. And then what do we expect will happen? Well, the bullet is gonna lodge itself into this block of wood. And then the combined system of the block of the wood plus the bullet will swing up in this fashion because it's connected by a rope to the ceiling, right? And the thing that we are trying to figure out in this problem is to figure out what is the speed of the bullet. This is a way in which you can determine, this ballistics pendulum is a way in which you can determine the speed of the bullet right before it hits this block of wood. So it's a very difficult problem, right? If you have some launcher and you launch a bullet, you want to figure out what is the speed of that thing. Here's one way to figure it out. Obviously, we know from our intuition that the greater the speed of the bullet, the higher this thing is going to swing up, right? So therefore, in some sense, by measuring the height of how much this thing swings up, we will be able to determine the speed of this bullet, and we will use two principles. One is that in this collision between the bullet and the block, it is a perfectly inelastic collision. They collide and then they move as one object together. So we can use the conservation of momentum in this perfectly inelastic collision. And then once they move together, this block plus bullet will have some total combined kinetic energy right after the collision. And all of that kinetic energy will get converted into gravitational potential energy, MGH, as it swings up, because it comes to a stop. So we will use conservation of energy. So we will use conservation of momentum in this perfectly inelastic collision. And then when they move together to determine how high it swings up, we will use the conservation of energy. And using those two principles, we will be able to figure out what is the speed of this bullet. Any questions on that? Okay, so let me just go ahead and collect some information here. Seamless, okay. So here's this picture to have in mind. We are told here that the mass of the bullet, M1 here, is 5 grams or 5 times 10 to the minus 3 kilograms. The mass of this block of wood is 1 kilogram. And they break it up into a part A and a part B just to kind of walk you through it. In the end, we want to find what is the speed of the bullet. But in part A, what they say is find the velocity of the system of the bullet plus the block right after the collision, right after they collide. What is the combined velocity of that bullet plus block system? And then in part B, we will figure out what must be the initial velocity of this bullet. So let's do part A. Oh, also we are told, by the way, that we don't know what is the initial speed of the bullet, so that's something we need to figure out. We know, of course, that the initial velocity of the block just before the collision is 0. It's just sitting there. And we are also told that this block swings up by a height of 5 times 10 to the minus 2 meters. So this is the thing that you will measure, how high it goes. And we are told it goes by 5 times 10 to the minus 2 meters. So let's look at part A. Here we want to figure out, find V system just after collision. That's what we want to find. Now, one thing you might say is, well, we could use momentum conservation. That is, we can look at the total momentum of this system before the collision. The block has 0 momentum, the bullet has some momentum. That must equal the final momentum. But the problem is you don't know what the initial momentum of the bullet is because you don't know what this initial speed is. That's what you want to find. So instead, we're going to use something else. We're going to look at the second part of this journey. Okay, we're going to look at the second part of the journey and use conservation of energy. So we will say, use conservation of energy after the collision, which says that the initial energy has to equal the final energy. The initial energy is whatever the initial kinetic energy is, plus whatever the initial gravitational potential energy is, has to equal the final kinetic energy plus the final gravitational potential energy of the system. What is the initial kinetic energy? Again, we're looking at the second part of the journey, right? So the bullet has hit the block. The two things now start to move as one. So right after the collision, the two things, as they're moving with one, they will have some speed that's causing it to swing up. So the initial kinetic energy will be 1/2 the total mass of the bullet plus the block, which is M1 plus M2. And it's going to have some speed, V system, that we're trying to find. So that'll be V system squared, correct? 1/2 mv squared. That's the initial kinetic energy. Plus, what is the initial potential energy? Well, we could just choose our y equaling 0 right over here. So therefore, it has no initial gravitational potential energy. Remember, gravitational potential energy is mgy. So if I just choose my y equaling 0 when the block is at the bottom, then the initial kinetic potential energy is 0. And then what is the final kinetic energy? As it swings up, it comes to a stop. So therefore, it no longer has any kinetic energy. So therefore, the final kinetic energy is 0. And now it'll have some gravitational potential energy because it has climbed up by a height h. And that is mgh. So in this case, that's m1 plus m2 times g times h. Any questions on that? And so you see now we have an equation here where we know h, we know g, we know m1 and m2, we can easily solve for what is v system squared. So therefore, I can write this as 1/2 m1 plus m2 v system squared is equal to m1 plus m2 gh. We see that the m1 plus m2 on both sides actually cancel out, and you get that v system squared is equal to 2gh, and therefore v system is the square root of 2gh, which you can now plug in numbers. Square root of 2 times 9.80 meters per second squared times the height was, I think, 5 times 10 to the minus 2 meters. Is that correct? Yes. And if you plug that in, you get that v system is equal to, let me just look ahead here, 0.990. So by seeing how high the thing went, we have figured out what must have been the initial velocity of the bullet plus block system just after the bullet hit it. And we use the conservation of energy. Let me add another page here. Now I'm going to come to part B, where we want to find the initial velocity of the bullet, v1 initial. Now notice in this perfectly inelastic collision between the bullet and the block, the kinetic energy is not conserved because it's a perfectly inelastic collision. The only thing that's conserved is momentum. So we will say that we will use momentum conservation in perfectly inelastic collision. And that says that the M1 V1 initial plus M2 V2 initial for the block, that's the total initial momentum, has to equal the final momentum, which is M1 plus M2 times this V system, right, that we just found. Any questions on that? Well, we know that V2 initial is 0 because the block was just sitting at rest right before the collision. So therefore, we are just left with M1 V1 initial, which is the momentum of the bullet, is going to equal M1 plus M2 times V system. And therefore, we can now solve for the initial velocity of the bullet as M1 plus M2 divided by M1 times V system. And now we can plug in numbers. M1 was 5 grams, is that right? M1 is 5 grams, which is 5 times 10 to the minus 3 kilograms. M2, I think, was 1 kilogram, all divided by 5 times 10 to the minus 3 kilograms. And then V system, we just found from part A was 0.990, 0.990 meters per second. And if you plug in those numbers, you get that the speed of the bullet, or the velocity of the bullet, was, let me look ahead here, 199 meters per second. Kind of an amazing thing that we were able to figure out such a detailed question after one semester of physics. Any questions on that? Okay, so that I think brings us to the end of the course material. I could keep going, but I think we're all tired. So I will stop the covering of new material here, and now we'll just do some top hat questions about from the test itself. I will kind of go over it here. We won't finish the test here in one day, so I will do it, part of it today and part of it tomorrow, or sorry, part of it on Friday. Any questions about any of this material so far before we switch gears? Okay. So let me just go ahead and add a page here. So I didn't have enough time to organize all the top hat questions. So let me start with the problems. And then we'll do the remaining problems and the multiple choice all in the next class. Go. Say it again?
We're going over the test.
Yes, that's right. So we'll start with the problem section, not the multiple choice. We'll do a little bit today, and then we'll cover the rest of the test tomorrow. And I think the point of it will be a bit of a review. It'll answer your questions about the tests. And I'll also give you some more pointers on how to write things out in your final exam so that I can give you more partial credit if you don't get the full correct answer. All right, so let's do problem 2. Oh, maybe I should have. Okay, I did not organize this properly. I'll be more organized on Friday. But let's do this first problem. Let me just write it out. It says that an astronaut applies a force. I should have just had a copy of the test on my iPad and worked on it, but it occurred to me right now, so sorry. I'll do that on Friday. A force of 5 times 10 to the 2 newtons to an asteroid. And the asteroid accelerates with a magnitude of 7 meters per second squared. It's given to us. And so then find the asteroid's mass. So the first thing is that, again, if you're on the final exam, you get a question like this. Resist the temptation to immediately start putting down numbers. The first thing you want to do is identify what is the concept that you're going to use here. The concept we're going to use is Newton's second law. So I'll write out here Newton's second law, which says that the net force on an object will always be equal to the mass times the acceleration of that object. And so if I just look at magnitudes, then I can remove the vector signs. Then the magnitude of the net force will be equal to the mass times the magnitude of the acceleration of the object. The thing that we need to find in this case we are given, so now that you have this concept identified, the thing you want to now look at is figure out is what are the numbers in the problem associated with in this concept. We are told that F net here, the net force is the force on the asteroid that the astronaut applies, is 5 times 10 to the 2 newtons. We are told that the acceleration of the asteroid is 7 meters per second squared. And the thing we're asked to find is what is the mass of the asteroid. So in fact, at this point, let me go ahead and make this a top hat question. Yeah, so again, let me just, so this is the question, have your test in front of you if you need to. Figure out what is the mass of this thing. And I will now make this a top hat question. So as you can see, I just put this together here. It's the problem we're currently talking about. Give your answer for the mass of the asteroid in SI units. So let's see what we got. The question is, an astronaut applies, yeah, there it is. Let me add a timer. Can you put the question back up? Are you guys able to still answer the top hat if I have this question displayed? You guys have access to the top hat? Yeah, okay. So I'll just leave this up, I guess. All right, let me go back. Let me open it up again, I guess. Yeah, so 50 seconds. Can you put the question back up? Oh, right, because the Zoom people don't have their tests. I see. I see the problem now. Okay, let me go back here. Okay, let's see what we got. All right, so looks like most of you got it. But again, a range of answers. So let me just work it out here. The thing we need to find is the mass. So now I can solve for the mass here. The mass is F net over the acceleration. Just coming from this equation here, I solve for the variable m. And so this gives me 5 times 10 to the 2 newtons divided by 7 meters per second squared. You plug in those numbers, and you get that the mass, I believe, is 71.4 kilograms. Any questions on that? So one of the things that I wanted to comment on is that this is kind of what I mean when I say on the test, show your work, show symbolic equations. There were quite a few tests where a lot of students knew how to do it, but they still got it wrong because I would have solutions like they would just go and write 7 divided by 5 times 10, and then they would get some number like that. Like that was their entire solution. So I think they knew to use this, but they messed up because they flipped these two things around. So they got the wrong answer here, and they got the wrong number. And with this, I just don't know how to give any credit, because you've gotten the wrong number and you haven't displayed to me any symbolic equations. You haven't shown me what your logic is or anything like that. And so I had to take a lot of points off for this. And so therefore, if you now had written this down and then you come here and you mess up the algebra and you say M is A over F net, and then you still get the same wrong answer, I'm much more likely to give you more credit, because I've seen that you identified the concept and you just kind of messed up here in solving for the mass. Well, any questions on that? All right, let's look at the next question. Maybe this is the last one we can do for today. So here we are told, let me write this in blue, I guess. So in question 2 on the test, a ball is launched from the ground with an initial speed of V naught equaling to 20 meters per second at an initial angle of theta naught equaling to 35 degrees from the ground. The question then is, how long does it take for the ball to reach its maximum height? So that is the question. The first thing I'll do is I'll underline how long does it take. Some of you try to calculate how high it went. And that's, again, make sure you read the question carefully. How long means how long it took. The first thing I will do in a problem like this, just to calm myself down, is to draw a picture so I know what's going on. Okay. Also, it gives you something to do so that you're not just panicking. You're kind of drawing a picture. It's a little zen, and it helps you mentally to see what's going on. So let me go ahead here, draw some. Here's my X and Y axis, I guess. I will launch this thing here. It has some initial V naught, some initial theta naught. That is what the launch angle and speed is. And we know that what's going to happen is that after it's launched, it's going to go off in some sort of an arc like this. And the question it's asking is, how long does it take for it to reach maximum height? Maximum height. Well, maximum height is right here. So we want to know this right here is the max height. Right. It also, if you draw something like this, it puts me in a mood to give you some credit, because it's telling me that you were able to process the word problem into what's going on, and you want to then figure out what is t? How long does it take to reach max height? And let's just collect some information here. We know that V naught here is 20 meters per second, and we know that theta naught here is 35 degrees. Now the second thing I'll identify is that this is a two-dimensional problem. So it's two-dimensional motion. So I have a set of kinematic equations that apply along the x direction, and a set of kinematic equations that apply along the y direction. So in principle, there's 6 equations that I could potentially use. And that can be, again, kind of intimidating, but you just stay calm and write them out. and then collect more information, think about it, and see which one you can use. So as you will see, it's actually a simple problem. You will just end up using one of them. But at the moment, you don't know that. So let me just go through the process here. So in the X direction, let me just kind of remind you here. Let me put this in green. This is our little box. For the general equations here, V equals V naught plus AT, either in the X or Y, whatever. You have X equals X naught plus V naught T plus 1/2 AT squared. And then you have V squared equals V naught squared plus 2A X minus X naught. You can apply this set of equations along X and along Y. So along the X direction, we know that AX is 0, right? There's only an acceleration here due to gravity with magnitude G. There is no acceleration along the X direction. So again, let me call this my positive X and my positive Y. So because AX is 0, along here, I know that I will get that basically Vx is equal to V naught X plus 0, because my AX is 0. And what is V naught X? It's just equal to V naught cosine theta naught, right? Because let me write this out here. This V naught here is this side here plus this side here. This is V naught cosine theta naught. This here is V naught sine theta naught. Is everybody clear on that? The X component of the velocity and the Y component of the velocity is that. Then over here, I will also get that my X is equal to, and again, I'm just kind of going through all the procedure here, knowing that I don't know. If you see it right away, you can go to the equation immediately. If you have enough practice, you will identify it quicker. But I'll just kind of go through all of it here. X is equal to X naught. We'll just say that this is your 0, 0. So your X naught is 0. So this X naught here is 0. Then you have V naught X, which is V naught cosine theta naught times T. And then this A here again is 0. AX is 0. So that's it. And then you have your last equation, which is just Vx squared is equal to V naught squared cosine squared theta naught. That's this V naught X squared. And then the AX here again is 0. So this doesn't contribute anything. So that's what I have. And then I can do the same thing in the Y direction. And here, my A, Y, is minus G. Because I've chosen my positive Y direction upward. The acceleration due to gravity is downward. So therefore, my AY will be minus G. So I'll just go here and I'll write Vy is equal to V naught sine theta naught minus GT. Now there is a way in which I can simplify this here. Does anyone see it? So what is the Vy here? It's referring to the Y component of the velocity at this final position here, which is at the max height. Right, so everything that's with a naught is referring to everything here, and everything over here is referring to the position, velocity, etc. when the projectile is at maximum height. What is Vy at maximum height? Anyone? 0, because it's going to go up, come to a stop, come back down. So therefore, I can replace this Vy here with a 0. And holy crap, I'm done. I have an equation here. Because the thing I'm looking for is the time. There was a time here that appeared, but I did not know what is the X coordinate when the projectile is here. So I could not use this time here. It would be X divided by this, but I have to first figure out what this X is. And I don't know that. That's not given to me in the problem. So your first guess might have been, I could have used this, but because I don't know X, I'm stuck. So I keep going, try to collect more information. But now here, I know V naught sine theta naught, I know G, I know T, and you can solve for T. And so therefore, you can now solve for T as being V naught sine theta naught divided by G. I'll make this a top hat question, see what is the answer. T is equal to what? Let me make this the last top hat question. So give your answer in SI units. So your time you want to solve for in seconds. I'll open up the question here. And let me make it 2 minutes for you to answer. And then I will come back here so you can still answer on top hat, but look at this. And again, the key here is in the final exam or whatever, if the best way, this is why I've given you the extra credit where you're doing like 40 problems or whatever, is if you do enough problems, then you get enough experience and you're like, oh, max height, that means Vy is 0. Therefore, that should immediately occur to you. And then with enough experience, you would just write that equation down immediately. But if it doesn't occur to you, it's okay. Then you just go through it step by step. And the final exam, you will have 2 hours. You should have enough time to complete the test. So time should not be an issue. So if you're panicking, just stay calm and go through it carefully. Questions on that? Let me see how people are doing. Yeah, so once you're done answering this question, class is over. Let me stop the recording here.